Hello everyone, welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is unilateral Laplace transform. We previously defined the bilateral Laplace transform. We discussed some of its properties, relevant theorems, region of convergence, and we presented some of its applications. In this lesson, we focus on a special case of Laplace transform, the unilateral or one-sided Laplace transform, defined as shown here. The unilateral Laplace transform is defined for causal signals only. And so when taking the inverse Laplace transform, we don't need to consider the region of convergence. This transform is well suited for analyzing causal systems modeled as linear, constant coefficient differential equations with initial conditions, non-zero initial conditions, that is. We will see how we can use the unilateral Laplace transform in circuit analysis. A difference between the unilateral and bilateral Laplace transform is in their differentiation property. Let's look at the unilateral Laplace transform of the derivative of a signal x of t. What we have is s times the Laplace transform of x of t minus the initial value of x at time 0. And if we take the unilateral Laplace transform of the second derivative, we get the expression shown here. S squared times the Laplace transform of x of t minus two terms involving the initial value of x at 0 and the value of derivative of x of t at time 0. And in general, for higher order derivatives of x of t, the Laplace transform takes the form shown here. The last term is the n minus 1th derivative of x of t at time 0. Assume that we have a causal LTI system described by the differential equation and the initial condition given here. And let's find the step response of the system using the unilateral Laplace transform. If we take the unilateral Laplace transform of both sides of the differential equation, we get the algebraic equation shown here. For a step response, x of s is equal to 1 over s. Next, we replace the values of x of s and the initial condition. We simplify the equation and get the new equation shown here. To get the step response in time, we take the inverse Laplace transform of y of s. Plotting the unit step response for different values of the initial condition, or alpha, starting with 0 initial condition, we have a growing exponential with steady state response of 1. As we increase alpha for values greater than 1, the step response will change to a decaying exponential with, again, the steady state response of 1, which is due to the unit step input signal. Knowing the Laplace transform of a signal, we can get the initial value and the final value of the signal. The initial value theorem states that if x of t and its derivative are both Laplace transformable, then the initial value of x at 0 equals the limit of s times x of s when s goes to infinity, provided that the limit exists, of course. Also taking the limit when s goes to 0 gives the final value of x of t, provided that s times x of s has no poles in the right half plane or on the imaginary axis. Let's find the initial and the final values of x of t given its Laplace transform defined as indicated here. Taking the limit of s times x of s when s goes to infinity gives the initial value, and taking the same limit when s goes to 0 gives the final value. If you look at the plot of the x of t, the inverse Laplace transform of x of s, also you can see how the signal changes over time and check the state of the signal at time equal to 0 and at the final time. The differentiation properties of the Laplace transform can be used to transform circuit elements so that the network analysis methods that we use, the nodal or the mesh methods, can be used directly in the transform domain. For example, for a capacitor where the current going through the capacitor is related to the derivative of the voltage across the capacitor in time domain, in the S domain, if you are using mesh methods, you can transform the capacitor as shown here. We have a capacitor with a new value and an input voltage source added in parallel to count for the initial condition. When using nodal method, you can consider the second circuit in the S domain. Let's use these transformations in an example. For a series RC circuit, we have the differential equation shown here modeling the circuit. X of t here denotes the input voltage and Y of t the voltage across the capacitor, which is the output signal. Given the values for the resistor and the capacitor and the initial voltage across the capacitor alpha, we want to find the unit impulse response and the unit step response of the circuit. Applying the Laplace transform to the component of the circuit, we get the new circuit shown here. Resistor is the same, and the capacitor has a new value with the current source connected in parallel with the direction shown in the circuit. For nodal analysis, the sum of the currents leaving the node between the resistor and the capacitor can be set to 0. And so we get the new algebraic equation shown here for the new circuit in the S domain. Simplifying the equation and replacing RC with 1 and the initial value of Y of t with alpha, we get the equation shown here, which can be solved for Y of s, the Laplace transform of the output signal to any input signal x of t. For the unit impulse input, we set the Laplace transform of the input equal to 1. Find the Laplace transform of the unit impulse response. The impulse response itself can be obtained by taking the inverse Laplace transform of this expression. Now for a unit step input, we set x of s equal to 1 over s, the Laplace transform of ut, and we find the unit step response in time. We can plot the impulse response and the step response together to see how they change over time. As you can see, when the initial voltage alpha is 0 or for values of alpha less than 1, we have a growing exponential for the step response and a decaying exponential for the impulse response. Increasing the value of alpha for values of alpha greater than 1, we get a decaying exponential also for the step response with the final value of 1. Another example. This time we are looking for the step response of the circuit shown here using the Laplace transformation, but for different values of the initial condition. First, with the zero initial condition. Zero initial conditions, we use the same circuit with a different value for the capacitor. Applying nodal analysis at the non-inverting input of the op-amp, we get the equation shown here. Simplifying the equation and solving for Y of s and replacing the values for the resistor and the capacitor and 1 over s for the step input x of s, we get the Laplace transform of the output as shown here. And we apply the inverse Laplace transform to get the impulse response in the time domain. Now, with non-zero initial condition, we transform the circuit into this new circuit with the current source added in parallel to the capacitor. The nodal equation at the non-inverting input of the op-amp again gives us this new equation. Simplifying the equation and replacing the values for the capacitor and the resistor and the initial voltage, we get the Laplace transform of the output equal to 0. The step response is identically 0. Let's look at one more example. Let's find the impulse response and the step response of the circuit shown here with the given values for the resistors and the capacitors and zero initial condition. Performing a nodal analysis in the S domain, for the node that is labeled as Vt, we get the equation here. Sum of all the currents leaving the node is equal to 0. And for the non-inverting input of the op-amp, we get another equation. So for this circuit, we have a set of two equations, and we solve them for Y of s and V of s. For the impulse response, we set x of s equal to 1, and we take the inverse Laplace transform of Y of s. And here is a plot of the impulse response. Now for the step response, we replace x of s with 1 over s and take the inverse Laplace transform to find the step response in time. Plotting the step response, we see that we have a growing signal starting at 0 with the steady state response of 1. In this lesson, we presented the unilateral Laplace transform as a special case of the bilateral Laplace transform. We showed how the unilateral Laplace transform can be used in circuit analysis, and we looked at several examples of finding the step response and the impulse response by applying the Laplace transform, basically transforming the problem into the S domain.